That's what we were supposed to do. I was going to call that.
Thank you for your attention. Welcome to the inaugural lecture of the Science and Society Distinguished Lecture Series. I hope you're not all here simply because you're afraid of what the end of sex might mean. I promise it's not as dire as it sounds, but it is truly our great pleasure to have Hank Greely here to kick off the series. If you're new to Science and Society is a campus-wide initiative that was launched last year and has a number of different programs that are offered, one of which is the Distinguished Lecture Series, which stems out of our Master's in Bioethics and Science Policy. There are great opportunities for undergraduates, for graduate students, and for faculty to get involved in different programs, from science communication to the understanding of the implications of science to society. There are classes that we offer. We encourage you to go to our website, scienceandsociety.duke.edu, to learn more about opportunities for engagement and upcoming events. We also encourage you to go there to read our blog. If you're interested in both reading the blog or in potentially participating as a blogger, we welcome people to be able to blog about current events at the intersection of science and society. And you can contact one of our two postdoctoral fellows, Abby Alina or Thomas Williams. Both of his contact information is there as an opportunity to be involved. So we encourage you to be involved and attend additional events. But I will only spend a minute or two so that I can leave the floor for Hank Greely, which is why I know you're all here, not just to hear about science and society. And it is truly such a pleasure for me personally and professionally to have Hank Greely here to kick off the series. Hank is a professor at Stanford Law School and somebody who is truly, as I describe, and love the description of, the godfather of the field of the intersection between law and the biosciences. So he is an expert whose expertise spans a great deal in this space, in genetics and genomics, and the ethical, legal, and social implications of ethics in genomics, in neuroscience, and in neuroethics. He's one of the original founders of the International Neuroethics Society. He was one of the co-leads of the MacArthur Law and Neuroscience Project, which has been an important project in the area of law and neuroscience. And he has a distinguished past working in both government as well as in academia, having clerked on the United States Supreme Court. He brings a great depth of experience and breadth of experience. And he serves on quite a few different national commissions and committees, including national academies and other ones where he provides important advice and input about the ethical, legal, and social implications of the biosciences. So without further ado, I will turn it over to him with one further note, which is a personal reason why it's a great pleasure for me to have him here as well, as he's a dear friend, and also was the officiant of our wedding with my husband. And so
I married Nita Farahani.
That's right.
I also married Theed Loader, but I don't talk about that as much.
And so among his many distinguished accomplishments, he also was a deputy in Charleston County, South Carolina. So without further ado, the end of sex.
Thank you. Although traditionally marriage isn't actually the end of sex, it may. Anyway, so thank you, Nita. It's a great pleasure to be here, and it is a great pleasure to be here both to kick off Nita's program, but also to be here at Duke, where you guys really have an amazing richness of people working in these areas at the intersection of bioscience and society and law and philosophy and medicine. I encourage all of you to take advantage of it, whether you're an undergrad or a graduate student or a faculty member or a staff member. There's a lot of talent here, a lot of interesting things going on. Get involved because it's important, it's interesting, and it's a lot of fun. And in fact, the end of sex, I hope, will be a lot of fun. Not in the sense in which you may be worried about. I don't think that the future I foresee is a future without sexual intercourse, however you and Bill Clinton choose to define that. And, you know, the problem with being a teacher for a long time is your references age out. Some of you weren't born when Bill Clinton got in trouble over that. I don't think it's the end of meiosis and sexual reproduction. I don't think it's the end of most of us identifying as either male or female. But I do genuinely think within the next 20 to 40 years, in places with good healthcare delivery systems, we will see the end of sexual intercourse as the majority way in which people conceive their children. I think we will see the end of sex as sex for reproduction as a majority choice in many places. And if you think about it, you can turn my title around and ask, what is the end of sex? Some people would say the end, the purpose of sex, is reproduction. I'm not willing to actually agree with that because I think lots of things don't have purposes necessarily. But I think this is the end of an end of sex. It's an end of one of the purposes of sex, sex for reproductive purposes. So what I want to do is first tell you a little bit about the technical advances that I think are going to lead to this end of sex. Second, tell you about what I think will be the cultural, social, political, economic, and other forces that's going to make what seems like a counterintuitive, almost dystopian vision become true. And then last, I want to raise what some of the ethical, legal, and social issues from this kind of society would be. And I hope to leave some time for questions on top of all that. So let's start with technology. I want to stress that what I am predicting, and this is a prediction, as Yogi Berra did not say, but Niels Bohr apparently did, it's always hard to predict things, especially the future. That's actually not true. It's easy to predict things. It's just hard to be right about them. I have a piece of advice. If you're going to predict something big and sweeping, set your time frame past your life expectancy. So in 20 to 40 years, and I'm willing to hope for the 20 years, but the 40 years is beyond hope. Sometime in the next 20 to 40 years, I think we are going to see these changes, and they'll be the result of two technical changes that we're already seeing. One is the vast improvement in our ability to do genome sequencing. The first whole human genome, and all of that should be in scare quotes, was sequenced around 2003 and cost somewhere around $500 million. Now, maybe it was $50 million, maybe it was $5 billion. Accounting is the darkest of dark arts. But it cost a lot. And it didn't get the whole human genome. There are parts of the human genome that we probably will never sequence because it's too complicated and there doesn't seem to be any reason to sequence all the telomeres or all the centromere. But it sequenced a lot. Today, you can get that same whole human genome easily off the rack. You bring in a sample and a check. The check clears $3,000 in several companies around the world. There are other companies that say they can do it for $1,000, which, again, accounting is tricky. If you buy the $62 million of Illumina equipment, you can then do a genome for $1,000. But the $1,000 genome is not far away. The $500 genome is probably not much farther away. I don't know what the bottom will be. Like all unsustainable trends, it will not be sustained. We will not see the millionth of a dollar genome. But we're seeing pretty cheap whole genome sequencing. Doing a pretty good job, and the accuracy also is likely to get better, needs to get better for these purposes, of doing whole genome sequence cheaply. We also know, because it's been done as proof of principle, that you can get a pretty decent whole genome sequence out of a single cell, or a small number of cells. And that you can get a whole genome sequence out of a single cell or a small number of cells taken from embryos, which opens up new frontiers for an old process called pre-implantation genetic diagnosis, better known as PGD, because that's a heck of a lot easier to say than pre-implantation genetic diagnosis. Some of you may even be the products of PGD. Most people think PGD is science fiction. PGD involves taking an embryo, taking one cell if it's a 3-day-old 8-cell embryo, several cells if it's a 5-day-old blastocyst, doing genetic tests on them, using that to conclude what kind of genetic traits that embryo would have, and using that to make a decision about whether you want to transfer that embryo into a woman's womb for possible implantation and ultimate birth as a baby. So PGD actually is now about to celebrate its 25th anniversary. First done in humans in 1989. First baby was born in 1990. It's not an old procedure. I mean, it's not a new procedure. It's not a novel procedure. It's been done largely for things like specific genetic diseases, looking to see which embryo and which embryos have inherited the bad allele for Huntington's disease, or in some places for boy or girl, or in some cases for will we have an embryo that can be a cord blood donor to our older daughter who is dying of leukemia. PGD has been used for all of these things. Last year in the United States, PGD probably led to the birth of about 4,000 children. There were about 10,000 cycles of IVF that involved PGD. So it's not new. It does have a track record. What is new, though, is instead of looking for one thing, instead of looking at the Huntington's allele, or instead of looking for Y chromosomes, boy or girl, or instead of looking for the HLA markers that determine whether or not you're a good tissue donor match, with whole genome sequencing, or something like whole genome sequencing, something equivalently dense, we can look at everything. We can do it today. It's too expensive to do it routinely. In 20 to 40 years, it will be trivially expensive. And so take a cell from a 3-day embryo and find out everything about it that can be deduced from its whole genome. I think that's going to happen. But there's still a major rate-limiting factor. In order to do PGD, you have to do IVF. Because in order to do PGD, you have to be able to hold on to and take a cell off an early human embryo. And if you have sex the old-fashioned way, at day 3, where's that embryo going to be? Partway down one of the woman's 2 fallopian tubes. Good luck finding it. Good luck getting it out. Whereas if you do IVF on day 3, that embryo is going to be in the same petri dish you put it in at day 0. It's going to be easily accessible. So IVF is necessary for PGD, not for any deep, dark reason, but just because if you're not doing it through IVF, you're not going to have easy access to the embryo. And IVF is a pain. I think it's probable that somebody in this room was born as a result of IVF. Not so much a pain for the baby. And it's not so much a pain except financially for the father. This is one of those areas where life is unfair. In order to do IVF, you need egg and sperm outside the body. Getting sperm outside the body is actually not a dangerous, difficult, risky, or unpleasant procedure. Maybe some hair shaving that's necessary later, but basically no one has been hospitalized as a result of sperm donation, as far as I know. Unless they were donating to somebody else's wife. Got caught. Egg harvest is very different. Egg harvest is an invasive procedure. It requires weeks of shots with powerful and expensive hormones. Egg harvest is responsible for over 80% of the cost of in vitro fertilization. It's responsible for about 98% of the discomfort of in vitro fertilization between injecting yourself with drugs and the side effects of some of those drugs. And it's responsible for all of the risk. Because about 1% of women who go through egg harvest every year in the United States end up hospitalized as a result. Now, this isn't the world's riskiest procedure. 1% is pretty low. And it's only every few years that somebody dies as a result of it. But there are women who die as a result of egg harvest. It's unpleasant, it's expensive, and it's risky. It's keeping down the possible use of PGD, because even though in theory you might want to pick some aspects of your baby's genes, if you have to go through IVF to do it, you need a pretty good reason, like trying to avoid Huntington's disease or trying to find a match for your daughter dying of leukemia. That's going to change because different breakthrough induced pluripotent stem cells are going to allow us to make gametes, eggs and sperm, from other cells. You guys, I'm sure, have all heard about human embryonic stem cells, first isolated by Jamie Thompson in 1998. You take an embryo, you destroy the embryo, you take the inner cell mass of the embryo, and you manage to culture those as cells that stay undifferentiated but can be turned into other cell parts. And you can use that to enthuse your core voters if you're a Republican or a Democrat. In the early 2000s, as a political issue, it's receding some, although it may come back. But one of the really interesting things that happened was a surprising discovery by a Japanese scientist, Shinya Yamanaka, in 2007, that he could take regular cells, skin cells, hit them up with a cocktail. In his case, he was using 4 genes, and turn them into things that look like embryonic stem cells. They're called induced pluripotent stem cells. They quack like embryonic stem cells. They walk like them. They talk like them. They look like them. They're not exactly the same. There are differences in how they develop. There are differences in what genes are expressed. These differences may or may not turn out to be clinically significant, but they hold open a really interesting possibility. Let's say my friend Bob Cook-Deegan has a heart attack. Sorry, Bob. You survive. That's the good news. The bad news is his heart muscle is damaged, and those cells don't come back. You get scar tissue. We could, maybe, the hope is, take some human embryonic stem cells, turn them into cardiomyocytes, the cells that are muscle cells for hearts, put them in Bob's system, have them go to the heart, and fix it. And if Bob were literally a rat, I'm not going to say whether you're metaphorically a rat or not. He's not. If Bob were literally a rat, we could do that and fix his heart. And he could run on his treadmill more.
Move up the anatomy here.
Exactly. Okay. No, hearts. But there could be a problem because those embryonic stem cells have a different genome from Bob's, and his immune system might attack them, requiring us either to put him on immune suppressors, which have a big set of problems, or face a situation where his immune system attack on his newly repaired heart makes things worse than they were to start with. If we instead take skin cells from Bob, turn them into induced pluripotent stem cells, turn those into cardiomyocytes, and put those in his body, presumably his immune system's perfectly happy. His welcome back long-lost twin brother. Because they've got the same immune system, the same cell surface markers, the same immune markers, no problem, so we think. So a lot of time, money, and effort is going into these iPSCs. It's not driven by anything having to do with sex. It's driven by diseases where we think that we can either learn something about the disease or treat the disease by making new cells that have a particular genome, the genome of a particular living person. And people are hoping to do this with nerve cells. So maybe that's moving up the anatomical chain for you, Bob. Heart cells, beta pancreatic cells, you name the cell, people hope to use iPSCs to fix a problem. Can we do it yet? No, at least not except in rats. Are we spending billions of dollars to try to figure out how to do it? Yes. Are we likely to be able to figure it out? I think so, because the incentives are so great. Now, so far I haven't said anything in this context about sex. But eggs and sperm are cells. Eggs and sperm started as embryonic stem cells in each of us. Eggs and sperm presumably can be made from induced pluripotent stem cells. It's just another cell type. The eggs are a little trickier than the sperm. They go through a really odd system of meiosis, et cetera. But it can be done. And in fact, it has been done in mice. Another Japanese scientist, Professor Saito from the University of Kyoto, a couple of years ago published in Cell that he had made sperm from induced pluripotent stem cells in mice, done mousy in vitro fertilization with harvested egg cells, made embryos, put them in, and ended up getting nice little mouse pups. The next year he had his publication in Nature, done the same thing with eggs. Turned induced pluripotent mouse stem cells into mouse eggs, fertilized them with regular mouse sperm, transplanted them, implanted them, and got mouse pups. The mouse embryonic stem cells were more successful than the induced pluripotent stem cells, so there are differences that need to be worked on, but he made it to work. I keep waiting for the next publication where he takes the stem cell-based sperm and the stem cell-based egg. I haven't seen that publication yet. I think he must be aiming for Science now, after having had Cell in Nature. The possibility that this could be done in humans, I think, is non-trivial. If we can do it in mice, if we're going to spend billions of dollars trying to make iPSCs useful for other cell types, I don't see any good reason to think we can't do it for gametes. I do think you need to be really interested in the safety. Because if we just put stem cells back into Bob's damaged heart, and Bob ends up, it doesn't work well, and Bob ends up with a more damaged heart, we're all sad. But we're not nearly as sad as if we use stem cells to make a baby, and the baby has some long-term problem. The baby never picked it. Bob has chosen to do this. So the safety issues, I think, get increased in significance when you're talking about making new babies than when you're talking about treating existing humans. But those are safety issues that can be studied and can be looked at. Let's assume this works. And in 20 to 40 years, we're able to make gametes, particularly make eggs, because sperm are relatively easy to get. We can then make embryos from them. We can then cheaply do whole genome sequencing on the resulting embryos. What's that world look like? I think it looks like a world where in places with good health coverage, couples who want to have a baby are going to start by going to a clinic, not start by going to bed or the back seat of a car or a park, keep off the grass sign. They're going to start by going to a clinic. She'll give some skin cells to be made into eggs. How many eggs? How many do you want? Right now with egg harvest, you're lucky if you get 12 or 15. Sometimes people only get 1 or 2. Sometimes they get none. Sometimes they get 20 or 25, but not very often. With this, you can make as many as you want. You then add sperm, either naturally acquired, or you could use the stem cell method for it if for some reason you needed to or wanted to. You make the embryos. You make, and the number I've been using because it's a nice round number is 100 embryos. You make 100 embryos. You sequence a cell from each of those 100 embryos. And you present the parents with choices. You cleverly name the 100 embryos 1 through 100. And you got a chart that has 5 columns. One column is really serious, highly likely to happen, nasty early diseases. Highly penetrant, bad, poor treatment options, things like today, say, Tay-Sachs disease. Children are born healthy, and within 3 or 4 years, they're dead from basically their brains turning to goo. It's a terrible, terrible disease. There's no good treatment for it. It's 100% genetic. It can be avoided. So column 1 is really nasty early onset diseases. There aren't that many of them. But about, depending on how you count, 0.5% to 1 or 2% of babies born every year have some pretty significant, predictable genetic disease. Column 2, other diseases. Things that are, say, later in onset. Predisposition to Alzheimer's disease. BRCA1 or BRCA2 mutation, predisposing a woman to breast or ovarian cancer. Lynch syndrome mutation, predisposing somebody in midlife to colon cancer. Or something more certain, but less serious, color blindness. You can test for most kinds of color blindness. I am differently colored. Greens look a little less vibrant to me than they do to most people. That's true of about 6% of American males. That's something that's in my genes that could be tested for. So second stage is diseases that are later in onset, that are lower in probability, or that are just plain less important. Category 3, cosmetics. Blonde, brunette, redhead, skin color, eye color, idea of height, rough body shape, male pattern baldness. Not looking at you, Walter. The positive trait of early white hair. The silverback gorillas rule those gorilla bands for a reason. It's the hair. All these things we know are heavily genetically affected. Now, they're not necessarily genetically determined. I could have my nice early youth dark brown hair back again, cosmetically. And my skin color changes color summer to winter a little bit. But they're heavily genetically influenced, and in some cases genetically determined. We don't know much about them right now, because the National Institutes of Health, which funds most of this research, isn't all that interested in things like eye color. It's not a disease. But as we get more and more sequence data and more phenotypic data and correlate it, they won't be simple, but they will be solvable at least to a large degree of resolution. So we can already predict whether you'll have light eyes or dark eyes. At some point, we'll be able to predict whether your eyes, which shade of light eyes and which shade of dark eyes. And if you imagine human skin colors in a book between 1 and 1,000, I don't think we'll be able to say, well, you're going to be, this embryo will be number 472. We'll probably be able to say it's somewhere between 465 and 480. Whereas this other one would be somewhere between 324 and 350. Something like that. So cosmetic traits. Category 4, behavioral traits. SAT scores. Sports, music, math, personality types, neurotic, extroverted, etc. My own guess is we won't do very well with those. I think they're too complicated genetically and too influenced by environment. I don't think we'll be able to say, this embryo, boy, 1580 on the 2-part SAT. The writing score you got to throw out, this grading's too screwy, but on the 2-part SAT, 1580. But I do think we'll probably be able to say, this embryo, 60% chance of being in the top half. 13% chance of being in the top 10%. 7% chance of being in the top 10%. 20% chance of being in the top 10% in music ability. And a bunch of behavioral traits like that. I don't expect any of it to be powerful, but to some people it might be enough to be a tiebreaker. And then category 5, the easiest one to test for, and one that parents often care a lot about, sex, boy or girl. So, you go to the clinic, you make eggs, you combine them with sperm, you get 100 embryos, you test the 100 embryos, you get a printout, and the clinic asks, so here are the 5 categories, which ones do you want to see? Do you just want to know about really serious early onset diseases? Do you just want to know about boy or girl? Do you want to know about cosmetics? Do you want to know about them all? Do you want to know about none of them? What do you want? And then you tell us which embryo or 2 you want transferred. Now, I do foresee as one side effect of this some serious problems in intra-couple harmony. Because he's going to say, I want number 12. That looks like Andrew Luck, the world's best quarterback and great former Stanford student. And she's going to say, I want number 66. That looks like, and take your choice, Hillary Clinton, Condi Rice, whoever, somebody that is really attracted to her. Prospective parents are likely to disagree. But they'll make choices. And I think mainly they will choose to avoid the serious genetic diseases. Some of them will want to do other traits. If you've got 3 embryos and they're all the same in terms of disease risk, you say, well, you know, this one has red hair. I always thought it'd be nice to have a daughter with red hair. Or this one, you know, there's a better than average chance that this one will be good at music. I'll use that as a tiebreaker. Parents will make different choices, but they'll have information to make choices. They will probably believe the information is more powerful than it is. I actually think one of the greatest, maybe the most valuable long-term effect of this situation would be people would realize that genes aren't as all-powerful as they think they are. And this wouldn't guarantee that kids wouldn't get whooping cough, or wouldn't get run over by a bus, or wouldn't have a terrible disease that's not genetic. But it adds some more control. In a sense, this is the Gattaca world. It's not entirely the Gattaca world, but it's a world where parents make choices between embryos based on their genetic traits. I need to make one really important point here, though. This is not a designer baby world. Because with 100 embryos, how many genes can you select for? Well, let's say there are 10 genes you care about, and each of them has 2 versions found at 50-50. If you want to get your favorite version of each of those 10 genes, you need about 100 embryos to have a decent chance to get one. To get one that matches on just those 10 genes. But there are 23,000 genes. There are probably 1,000 genes involved in intelligence. We can't get perfect babies this way, or perfect. We can't get our choice of the genotype of the baby we want. To do that, we'd have to do genetic engineering. That's a different story. I think that's farther off in the future because there are higher risks, I think, for it. But this is selection. It's not selection from all the alternatives. It's selection of a subset of the alternatives that the two of you who want to make this baby have in your genes to present. If you both have dark eyes, you can't have a light-eyed baby if you're using your sperm and your eggs and not doing anything genetically to it. So you're limited in part by what you two bring to the table, or bring to the petri dish in this case, and limited in part by what chance throws up in the 100 embryos you get. So most people think of Gattaca as kind of a dystopian movie. Is there any chance that this country would actually move to a society kind of like that? I think the chance is very, very high. And this is the second part of the talk, what the social, economic, political, and other forces will be. How is this going to happen? First, the key breakthrough here is making gametes, making eggs from iPSCs. And I think that will happen for reasons that have nothing to do with PGD and have everything to do with the several million Americans who desperately want to have kids and can't because they don't make eggs or they don't make sperm. If you're born without eggs or sperm, you can't have a, quote, child of your own, close quote, a term I hate, because I think adopted parents' kids are their kids, but you can't have you can't have your own 50% genetic child. The best you can do is get a sib to donate eggs or sperm, and you've got a child who's 50% genetically from one parent and 25% genetically similar to the other parent. To have children that are your genetic children is a very strong urge in many people, which is why people spend thousands of dollars and much toil and torment and mental anguish in IVF. And there are people for whom they can't do that even with IVF because they don't have eggs or sperm. That's going to be the first target. I have a friend, Renee Rea-Hopera, was at Stanford, now went to Montana, who works on this. And she says every week she gets emails from people saying, can you help me? I understand you're working on making eggs and sperm. Can you do that for me? And she has to say, well, maybe in 20 or 30 years, but not yet, unless you're a mouse or a rat. So that's what's going to start. Once the FDA approves it for one purpose, though, under federal law, something approved for one purpose by the FDA can be used by a physician for any other purpose. And I think you'll begin to see then people who need to go through IVF for some other reason, blocked fallopian tubes, saying, why should we go through egg harvest and the risk and discomfort and unpleasantness of all that and the expense? Let's just make some eggs from skin cells. And then someone will put it together, presumably someone who has bought my book and paid the full price, and say, well, let's do it for easy PGD. So I think it will slip in as a fertility treatment for people who don't have their own gametes, and then broaden out its use. How broad will that use go? I don't think we'll ever get to the point where everyone will use it. Some people will have religious objections. I think many of them will be old men in the Vatican who probably weren't going to have children anyway, but there will be some other people who share this religious objection. Some people will have philosophical objections. Some people will just say, you know, it's so much more romantic to just have sex and roll the dice. And some people will be dumb teenagers who get pregnant in the backseat of, who as a couple become pregnant in the backseat of a car and aren't thinking about anything in particular at that time. There will be people who won't use this. If it's expensive, there will be more people who won't use this. But my bet is it won't be expensive, at least not to the couples. I think it will be free to the couples, because from a public health perspective, it will be a cost-effective intervention. Let's say, and you know, to guess about healthcare costs or prices today is a fool's errand. To do it 20 or 30 or 40 years in the future is a fool's errand to the 20th power, but I'm going to do it anyway. Let's say the whole process costs $10,000 for every baby you make, which I think is, you know, maybe on the high side, but probably in the right area. Make 100 babies, that costs you $1 million. How many really sick babies' births do you have to prevent to save $1 million? About 0.3. If you only prevent a couple of births out of 1,000, the process is cost effective. Now, that may or may not mean anything to the parents involved, But whoever's paying the health insurance bills, whether it's a company or a government, that's going to be significant activity. Now, in the U.S., there are stronger religious and political issues. Many of them revolve around abortion, dealing with reproduction. One of the things that's interesting about this is no fetus is killed. Now, from some perspectives, not using a fertilized egg, not using an embryo, is the same as murder. But there are a lot fewer people who believe that in the United States than believe killing a fetus is murder. The political power against IVF is not very strong. The official Catholic doctrine is IVF is sinful. It's actually doubly sinful and should not be allowed. No one is campaigning in the U.S. on banning IVF. The politics of IVF, of not aborting, and of helping people who want to have babies, is really hard for the pro-life movement to object to. PGD will be trickier. Most people will not object to using easy PGD to avoid serious birth defects, although some will. More people would object to intelligent selection or sex selection, and interestingly, that'll span various parts of the political spectrum in interesting ways. But my guess is the U.S. will continue its position of being the developed country with the least regulated assisted reproduction system in the world. Ours is basically unregulated. The IVF clinics will say, no, we regulate ourselves. We've got all these files. Ours is unregulated compared to the rest of the world. And I think that's a reflection of some of both the libertarian and the political instincts in America. And I think that's going to continue. So I think, starting with fertility for people who are agametous, who don't make gametes, adding in available to everybody because it's cost effective, adding in American politics and a reluctance to interfere in private reproductive choices, I think this is going to happen. I think if the science happens, if the medicine happens, it will socially happen, and I think it will happen in the United States. But if it doesn't happen in the United States, and it's scientifically possible, it will happen elsewhere. Singapore, People's Republic of China. There are places where it won't happen. Italy, probably not anytime soon. Germany, may well not anytime soon. They've got an allergy, an induced allergy from the Nazis to a lot of this work. But there are countries that will adopt it more heartily than the U.S. and countries that will adopt it or not adopt it at all, less than the U.S. Someone will do it, even in the U.S. It's possible that Mississippi or North Dakota will decide not to allow it, or to allow it only for some indications but not others. Not California, not Nevada. Be a new source of business for Nevada. Reproductive tourism, which already exists, will be an issue both domestically and internationally here. So I think this is going to happen. What follows from that? What concerns should we have about a world with widespread use of easy PGD? I think they fall into 4 or 5 categories. The first and most important, for me at least, is safety. Safety of the children born this way. Because how long will it take us to know whether it's safe to make a baby out of an iPSC-induced derived egg? Well, the answer is a hell of a long time. How safe is IVF? There's still some quibbles about whether it raises risks of some relatively rare diseases. It does have a big health risk from multiple births. Twins and triplets are less healthy, and IVF tends to increase the number of twins and triplets in ways we could easily deal with, but won't, or haven't so far in the U.S. Other than that, it looks pretty healthy, looks pretty safe. But it is possible that every person in the world born as a result of IVF could drop dead on his or her 37th birthday. Because Louise Brown, the oldest IVF child in the world, just turned 36 this year. Maybe IVF leads to early Alzheimer's. We wouldn't know yet. Maybe there are other health issues. And we don't know very much about IVF because we didn't track the kids' health in a very sustained way. So I think we need FDA or its equivalent regulation to make sure this is healthy, starting with in vitro work then moving to animal work, probably requiring work with some of the other great apes, which is always tricky financially, ethically, and in other ways to do. But I think you want more than rabbits and mice before you decide you can do this in humans, at least macaques, if not apes. And then eventually going to some human clinical trials where there are parents who volunteer, and they volunteer themselves and they volunteer their unborn child to be experimental subjects here. I think, and why I say 20 to 40 years is not the science. I think the science could be here within 10 years, maybe even shorter. I think you need at least 10 years of safety testing, of regulation, before it would be anything other than reckless to try this. Having said that, we don't have a single stem cell approved embryonic stem cell therapy in the United States. But there are scores, if not hundreds, of clinics around the world that will gladly take your money and give you stem cell treatments for all sorts of things. Some, I think, actually believe that they can treat you. Some are just frank frauds and quacks for whom the death penalty is too good a punishment, in my view. It'll happen with this. There'll be renegade, easy PGD clinics in countries with limited interest in keeping foreigners from spending money in their country and taking sick babies, potentially, back home. So I think there's both the question of regulating for safety within a system and then worrying about the outliers, the clinics that do it even though it is crazy and reckless. I think the safety issues are really big. Another set of issues that I think are interesting, maybe not so big, are family relationship issues. Let's go back to the Andrew Luck couple. The guy wins. They make Andrew Luck. But it turns out that rather than want to play quarterback for the NFL, he instead wants to be an architect, which actually is what the true Andrew Luck wants to do once his NFL career is over. Or he wants to be a poet. He doesn't like football. He doesn't want to play football. Now, how many of you are parents? How many of you had your kids turn out exactly the way you expected? Right. They're always going to surprise you. Right now, we try to guide our children in certain directions, and sometimes they go and sometimes they don't, and our degree of control is limited. Genes aren't going to change that much, but what they may change is the parent's expectation of control. Damn it, I picked you to be a quarterback. Go play football. Instead of, I want you to go to be a quarterback, here's a football, go play with it. Will that change family relationships? I had a student once who said, the worst thing would be from the kid's perspective. Think of the invasion of privacy. My parents knew all my genes before I was born? That seems worse than reading my diary. So there could be tensions both ways. You also get other issues. If you can make eggs from skin cells, well, yes, women between 15 and 40 have skin cells, but so do women after 40, or 50, or 60, or 70. The biological clock may disappear in both directions. 5-year-old little girls have skin cells too. You could make eggs from those. You could make eggs from frozen tissue, from people who have been dead a long time. You could make eggs from people from whom you managed to get a little bit of a cell sample. Now, to get a sperm or an egg sample from somebody is tricky. Bob has just left lots of living cells, most of them dead, but some of them living, on this desk. And if you throw away a Diet Coke can, you got living cells on that Diet Coke can. Could I use those to make you a parent without your knowledge? Or, since these are cheap, could celebrities start selling their eggs and sperm made this way? Would we put any limits on how many kids they could have? Should we put any limits on it? And two other quirks. There are a lot of couples in this country and around the world who can't have, quote, children of their own, close quote, because although they make gametes, they both make the same gametes. They both make sperm or they both make eggs. If you're a lesbian couple and you really want to have a baby, right now the best you can do genetically is to get the brother of one of the couple to donate sperm. If we could take skin cells from one of them and turn them to the other sex's gametes, make eggs from men's skin cells, make sperm from women's skin cells, It opens up new possibilities for new types of families. That will play very, very poorly right now in some parts of the country. But I can tell you, as somebody who lives near the city and county of San Francisco, it would play really, really well there. There's a lot of political support, money, and interest in people who unfortunately have the same gametes wanting to have genetic children. Last of these, and I never thought of this till one of my colleagues at the law school brought it up, and I think it's perhaps not a coincidence that this incredibly egomaniacal thing was thought up by a law professor. So we'll go to Nita. If we can make eggs from women and eggs from men and sperm from women, so we take some samples from Nita, we make them into induced pluripotent stem cells, we make some of them eggs and we make some of them sperm, and they're both from Nita, and we merge them together. We have mini Nita, mini me. Note, it's not a clone. Cloning is another technology that may or may not go anywhere. Every place she's homozygous, every place she's got two of the same allele, the baby will be identical to her. But wherever she's heterozygous, where she's got, say, a type A blood type gene and a type O blood type gene, the baby has a 50-50 chance of being AO, and a 25% chance of being AA, and a 25% chance of being OO. It won't be exactly Nita, but it'll be closer to Nita than her sisters are, at least genetically. So all sorts of family relationship conundra are possible here. I think those are interesting. Those aren't as important to me as safety or the next two. One is equality. One issue with equality is economic equality. There are people who think we'll have a stratified caste system with supermen and submen, with the Eloi and the Morlocks, although I'm not sure that works well because I'm not sure who actually was the better there, from The Time Machine by H.G. Wells, a book I highly recommend. I don't think so, in part because I think it will be free, and in part because I don't think all these genetic advantages are actually going to be that big a deal. You're not going to get supermen. You get slightly healthier kids. Probably not as much healthier as the difference between being born in the lowest quartile of the income stream and the difference from being born in the upper quartile of the income stream, where the amount of care, nutrition, et cetera you get leads to different health outcomes. So I don't think we have to worry about a genetic caste system. But the income differential is potentially troubling, I think, as is the income variation currently in our society. I don't want to make it worse. But if it's free to everybody, it won't be. But even if it's free to everybody in the US, it's going to be a long time before this becomes standard operating procedure in the Democratic Republic of the Congo, except for the 1% that's really rich, or the back country of Paraguay, or central Laos. There are going to be global inequities based on income, even if within rich countries there aren't. There are also other potential inequity issues. What happens, let's say, if there are certain ethnic groups that are less likely to take advantage of this? So in California, where prenatal testing for Down syndrome must be offered by law to every pregnant woman, we find that Hispanic women are much less likely to take it than non-Hispanic women. And actually, after you control for Catholic versus non-Catholic, that doesn't matter. It's not religion. It's something about Hispanic culture in California makes a woman less likely to be interested. Well, if that meant that most of the children born with Down syndrome in the United States were Hispanic children, that could cause some tensions. It could cause some ethnic and political concerns and sets of inequality. I think the deeper issue, though, is more one of disability issues. I think the disability issues in some ways are the hardest here. I was given a talk related to this. It was before the idea of easy PGD came to me, so it was just PGD. Several years ago, and a Stanford graduate, woman who was about 30 at the time, was on one of the panels. She worked for a disability rights organization. She had spinal muscular atrophy. She's in a wheelchair. It's a genetic condition. She'd been in a wheelchair for a long time. It was getting worse. Perfectly lovely, brilliant young woman. She said, "What you're saying is I shouldn't have been born." And I said, "Gosh, I hope I'm not saying that exactly. But I think what this says is if you adopt it, your parents should have had a choice of having an embryo that had your genotype and an embryo that didn't have your genotype and didn't have your disease." And so, yeah, you wouldn't have been born, but then you wouldn't have been born if a different sperm had managed to fertilize that egg. Or if at the age 2 your dad had lost his job and you'd moved to a different place, or you'd been hit by a truck at age 5. There are all sorts of things that go into making us who we are. And yet that emotional hit, the jolt I felt when she said, "You're saying I shouldn't have been born," is hard to deal with. There's a non-psychological side to it, too. If you say, are a person with Down syndrome, or a parent of a person with Down syndrome, or a SIB, and you expect there will be far fewer people with Down syndrome born in the future, what's that do? It makes your loved one with Down syndrome stand out more, probably in a negative way. It decreases research funding, probably. It decreases political support. It decreases social support. It's bad for people who've already got this disease, or for subsequent people born with the disease because their parents either didn't use the process or didn't opt for this to opt out of this particular disease. I think the disability issues are really serious. The other issue that I think in short term, 10 to 15 years, is quite serious is sex selection. It doesn't look so far like a big problem in the US, but in many parts of the world, parents given a choice much prefer a boy than a girl. It does look, frankly, in the US as if people want to have the first child a boy and the second child a girl. They want balance, but they want the first one to be male. There are parts of the world where there are 20% more males than females. And it's thought that this could be a serious problem. And there are already parts, Alaska has more men than women. The American frontier had more men than women. There will be issues raised. This will potentially exacerbate it. So I think there are a lot of equality issues. Fourth, coercion issues. I don't think it will ever happen in the United States. But I can imagine quite easily there are countries that would say, everybody has to go through easy PGD, and no one will be allowed to implant any fetus, any embryo that has a projected IQ below the midline, or that has any of these diseases or risks of diseases. We only want good babies here in name your own favorite whipping boy country. Democratic Republic of Korea comes to mind, perhaps. But it doesn't have to be that much of an autocracy to say, we want to use this, and we want to use this to make our population better. It's a public health measure. You Westerners sneer at us and call it eugenics, but you vaccinate people against their wishes. You test little kids, babies, for genetic diseases that you can do something about. We're just trying to make our population better. Some countries will do that. I think the interesting flip side is it coercion when a country says you can't use it? You, the parents, are not allowed to use it. That's coercion, too. We don't necessarily think of it as coercion, but you're being prevented from doing something that medically you could do. And maybe the most interesting slot is, OK, you can use it for serious diseases, but nothing else. You can't use it for sex. You can't use it for hair color. Only serious diseases. Now, part of the underlying idea here is with whole genome sequencing, it's the cheap and efficient way to do this. You get all the information. But either parents aren't allowed to use it, or more likely, parents have that information kept from them so the doctors can only reveal the relevant information. I think that sounds to a lot of people kind of appealing. You can use it to avoid Tay-Sachs. You can't use it to avoid color blindness. But then you've got the government in the position of saying, OK, these people's lives, we can understand where parents would say they're not worth living, but these people's lives are worth living so much that we won't let parents make a different decision. And do we really want the government making that choice? Politically, will the government be able to make that choice? I think it's an unstable political situation, as well as a very, very difficult ethical and moral situation for the government to be choosing between people, as opposed to parents choosing between people. It's tough in both situations. I think the coercive aspect of it, coercing the parents into what kinds of choices they can make about children, makes it more complicated. Well, there are a variety of other interesting issues, but I think issues of safety, family relationships, equality, and coercion are the main headings to worry about. What should we do? Beats me. This is a book, or it will be a book. I'm at halfway through chapter 17. Nita is probably snickering because I've been halfway through chapter 17 for at least 2 months now. It's only an 18-chapter book. I'm almost done. have to rewrite it all from the start, but almost done. My editor wants me to take a position. I'm reluctant to. I'm more inclined to play the lawyer and say, look, readers, as parents, as grandparents, as lawyers, doctors, obstetricians, reproductive endocrinologists, taxpayers, legislators, you need to think about this and decide what you want to do. If North Dakota wants to do something different from California, I'm not sure I care. If North Korea wants to do something different from California, I might care, but I might not. People have different moral codes and different sets of concerns and interests in different cultures and different parts of the world. I'm tempted to just lay it all out and say, okay, here are the pluses and minuses of each option. Your choice. Do you want to plead guilty or do you want to go to trial? Do you want to ban it? Do you want to partially ban it? Do you want to encourage it? How do you want to play this? But if you held a gun to my head and coercively said, no, we need to know what you think, as one person's opinion, and that's all I put it forward as, I think the least bad alternative is to let parents choose. Some parents will make a hash of it. They do already. Some parents will do bad things. Some parents might even choose to have a child with Tay-Sachs disease. I can't imagine why, but it's a big world, and there are a lot of crazy people out there. And I think that would be a bad result. And yet, on balance, I think parents are more likely to know to want what's best for their kid. They may be wrong about what's best for their kid, but they're more likely to want it, and they're more likely to actually have some idea of it than a government or a consensus conference of physicians or an individual physician or anybody else. I would be hard-pressed if somebody said, yeah, but here are these parents who want to make a baby with Tay-Sachs. That would be very hard for me to say, yeah, they should be allowed to. But I think on balance, that's probably where I come out. But it doesn't have to be where you come out. I do think this or something like it is going to happen. I think we are already seeing and will continue to see because of technological breakthroughs having very little to do with reproduction. Fast genome sequencing isn't for reproductive purposes. iPSC research isn't primarily for reproductive purposes. This is a secondary use. But it has a secondary use in an area we care about very much. So I charge you, you are now among the 1,000 people in this world who know the most about EZ-PGD. So 0.0001% or something. Think about it. Pay attention to it. Read about it. Follow these developments and think about what you would do. For some of us, it's not my direct issue. It might be my kids and will be my grandkids. For some of you, you could be parents using this. What should you do? What should we do? Because really, at stake in some respects are some of the future directions of our entire species. Thanks for your attention. I think I've left 10 seconds for questions.
We also have a reception immediately following for the next hour out here where you can ask additional questions. So we can